Good day, everyone. We are Min Min, Rachel, Sydney, and Chelsea from Tortilla Turtles. One bright and sunny day, soccer players Bob and Tim were turned into robots. In order to still be able to play the sport they love, Bob and Tim turned to Tortilla Turtles for help to solve their predicament, allowing them to add sensors and other components to help them play soccer again, and even better than before.
Min Min and I, who are in charge of the software, added and modified the code of the two robots, allowing them to think more logically and play soccer better. Sydney and Chelsea, who are in charge of the hardware, were able to attach multiple sensors to allow the two soccer players to understand their surroundings better. They also modified the wheels of the robots so they could move more freely and efficiently. Without further ado, let's continue the story.
Tortilla Turtles had to use LEGO Mindstorm EV3 to build and program the robots due to our limited time span of 4 months, which made it harder to procure non-EV3 materials. Furthermore, most of the EV3 sensors and motors are already available in school, with the exception of 𝗈𝒐𝒃𝒂𝒑𝒐𝒄, so we did not have to buy new sensors or motors, reducing our budget.
As Bob looked down at himself, he realized he was made out of many interesting components: the ultrasonic sensor, the 𝗈𝒐𝒃𝒂𝒑𝒐𝒄, the multiplexer, the gyro sensor, the omni wheels, and the ball capturing zone. Wait, why does Bob have 4 wheels? Don't normal human soccer players have 2 legs?
Well, for 2 wheels, if the robot wants to move left and right, it needs to tilt itself such that its wheels face either side and move, which is very inefficient. So if we have 3 or more wheels, we give the robot 360 degrees of freedom to move without tilting. But if the robot has 3 wheels, assuming each wheel applies 1 Newton in the direction of the orange arrows, there would be a net force of just 1.73 newtons. As for 4 wheels, the net force is 2.83 newtons instead, which is more than 1.5 times the force applied for 3 wheels.
I see. This means with 4 wheels, the robot can move faster. So this is preferred over 3 wheels. Of course, adding more wheels means increasing the net force, but the maximum number of wheels the robot can have is 4, as there are only 4 motor pods in the EV3 brain, so it went with 4 wheels. Okay, but why does Tim have 4 omni wheels instead of normal wheels?
Omni wheels have rollers which are perpendicular to the direction of their main wheels, so they allow the robot to move all 360 degrees without the robot having to tilt.
And with the wheels settled, let's look at the coolest base ever. The base of the robot is wide and flat, which means they would not topple over easily. The center of gravity is also very low, which means that the robot is less likely to fall when traveling at a high speed, being hit by other objects, or coming to a sudden stop. The motors are placed perpendicular to each other, in the shape of a cross, so the motor can turn in the same plane as the wheels, reducing the need for flipping of planes, which can add more weight to our robot.
And as you can see, our robots are quite rigid and do not fall apart easily. This is because we use acrylic to brace the wheels to ensure that the wheels do not fall off easily when traveling at high speeds. Acrylic is melted and bent into a 90-degree curved bracket. We also ensure that the robot is symmetrical so that it will not tilt to one side too easily, like the Leaning Tower of Pisa. Furthermore, since the brain is the heaviest component of the robot, there are a total of 8 points connected to the brain and the base to ensure that it is securely attached. Lastly, there are cupboards around the base to absorb shock from collisions when the robot hits the ball or another robot, which protects the components inside. Oh look, the robots have sensors. Why are these sensors chosen again?
Well, the ultrasonic sensor senses the distance between the robot and the wall, allowing for localization. This means we need 2 ultrasonic sensors per board in total, 1 on each axis. The robot needs to know what direction it is facing, of course, so we need 1 gyro sensor. Lastly, we also have to be able to sense the IR ball all 360 degrees of the board. So we need 2 or more IR sensors as one IR sensor can only sense 240 degrees.
Wait, doesn't this mean we need 5 ports, but the 𝑰𝒏𝒇𝒍𝒐 only has 4 sensor ports?
That's where the multiplexer comes in. It adds 2 extra ports to 𝑰𝒏𝒇𝒍𝒐, making it 6 sensor ports in total. Problem solved!
I see. That means we have 1 more sensor port. What should we do with it? I know, we can add a sensor angled down to detect the ball at the ball capturing zone. Color sensors are not really reliable since their readings can be affected by external light sources. Let's use ultrasonic sensor instead. As long as the robot doesn't topple, which is already prevented by what we mentioned earlier, the distance will be consistent.
Let's try to fit the ultrasonic sensor here, slightly tilted downwards. This won't block the front ultrasonic sensor and the front IR sensor. And also, let's make the ball capturing zone a 90-degree V shape. This increases the area the ball can catch the ball, and also brings the ball to the center.
Great thinking! I don't think the ultrasonic sensor is super necessary for the goalie though. Let's add a color sensor pointing towards the field to the goalie instead. This makes for a more accurate boundary control, don't you think? I think the hardware looks promising. Let's pass it on to Min and 𝒣𝒑𝒈 to discuss the software.
Oh no! Bob and Tim are clueless as to how to play soccer. Time for us to put our coding skills to test, 𝒣𝒑𝒈.
Indeed. Let's first start with moving. We need to coordinate all 4 wheels to steer in the intended way. Let's create a steer function. Bob and Tim just need to input an angle or the direction they want to move to according to angles on the compass. For example, 70 degrees. Next, we define our X and Y axis to be as such, with the X axis being controlled by the top right and bottom left wheels, and the Y axis being controlled by the top left and bottom right wheels. Then 45 degrees is subtracted from the angle to make 0 degrees fall on the y-axis. And now we can apply trigonometry. So as you can see, the robot needs to move in the direction of the x-axis by sine 25 degrees and in the direction of the y-axis by cosine 25 degrees. And voila! Bob and Tim can now move in a certain direction accurately.
That's good to hear, but look, they deviate more and more from the fronts by the second. I mean, no robot is perfect, so we can't assume our robot is always facing the front.
I agree. Facing the front ensures the accuracy of the readings of the ultrasonic sensor, which allows for accurate localization. Furthermore, due to the shape of our ball capture zone, if the robot does not contact the ball while facing the front, the ball can easily roll away. And I'm sure Bob and Tim wouldn't want that, right?
Introducing Rotating with Steer function. This is basically Steer function 2.0, where the robot not only moves in the intended direction, but also corrects itself to face front. My explanation will be based on one axis, but it can be applied to the other axis too. So there are 4 possible cases of correction we have identified. Case 1. The angle inputted earlier is in the top half, and the robot needs to make a positive rotation, that is, the robot needs to turn right. In this case, without rotation, both wheels will be moving in a positive direction. So, for a positive rotation to happen, the left wheel must move even faster, or the right wheel must move even slower. Therefore, the left wheel must be moving at a faster speed, while the right wheel must be moving at a slower speed. Using a similar logic for cases 2, 3, and 4, we can derive which wheels are moving at a faster speed and which wheels are moving at a slower speed.
But how are the fast and slow speeds calculated? We don't want too huge a speed difference when the rotation is small to prevent overshoot. Neither do we want the robot to rotate too slowly when the rotation is huge.
So that's why we need proportional rotation. When the rotation is small, we can decrease the rotational rate, thereby decreasing the speed difference between the fast and slow wheels, and vice versa. And this results in this equation right here. This equation works as when the rotational rate is 0%, the slow speed is equivalent to the fast speed, which results in no rotation. Conversely, when the rotational rate is 100%, the slow speed is a negative of the fast speed, which results in the fastest possible rotation. Such a useful equation, isn't it?
Indeed, I'm sure Bob and Tim can move more easily now.
𝗏𝒑, I noticed you mentioned localization just now. What exactly is it?
Well, the robot needs to know exactly where it is on the field, so as to retreat from boundaries if required, or be able to move to a certain position it wants to. We can leverage the front and right ultrasonic sensors on the board. Defining 0, 0 as the bottom left corner. To get the x coordinate, we can add up the right ultrasonic reading and the distance from the right ultrasonic sensor to the center of the robot, and subtract this from the breadth of the field, which is 182 centimeters. Similarly, to get the y coordinate, we can add up the front US reading and the distance from the front ultrasonic sensor to the center of the robot, and subtract this from the length of the field, which is 243 centimeters.
But as you can see, the robot's location fluctuates quite often, especially for the y-axis. This could be because sometimes the front US is seeing the goal instead of the wall, which reduces the distance it's supposed to sense. How do we solve this problem?
I know. There are two ways we can go about doing this. Firstly, we can take the highest reading of the last few readings of the ultrasonic sensor to try to ignore the readings of the goal. However, a caveat of this is that our runtime will significantly increase, making the robots less responsive to sudden changes. Therefore, we must strike a balance between runtime and the accuracy of the ultrasonic readings to achieve the most optimal performance.
And the second way is to subtract the distance between the goal and the wall directly from the front US reading before doing any processing, right?
Yes, you're right. Now that we have achieved a somewhat reliable localization, let's move on to one of the highlights of our software, ball following.
Just a recap, our robots have two IR sensors, one facing the front and one facing the back. Each IR sensor can cover 240 degrees around the robot, so there are overlapping regions covered by both IR sensors.
To follow the ball, the robot cannot just blindly move in the direction of the IR ball, or it will not contact the ball at the front, where the ball capture zone is. Therefore, when the ball is between 0 degrees and 90 degrees, the robot will drive at twice that angle.
And when that ball is between 90 degrees and 180 degrees, the robot should not be moving at twice that angle, or it will move in a big circle. Instead, the robot drives at that angle plus 90 degrees, so that it efficiently moves to contact the ball while following the ball from behind at the same time.
Yes, and a similar analysis is done for the other side. The only difference is that the robot moves in the opposite direction. Min, I think you mentioned just now that there are overlapping regions covered by both IR sensors. Why are they at the sides and not the front?
Well, putting them at the sides allows us to tell when the ball is directly beside the robot or when the ball is at a certain distance from the robot. When the ball is directly beside the robot, or when both the IR sensors are sensing a high intensity at 60 degrees, 120 degrees, or 240 degrees and 300 degrees, we need to increase the aggressiveness of the ball following function. In other words, draw a slightly bigger circle. so as to be able to contact the ball from the back without accidentally hitting the ball. Other times, the robot can draw a smaller circle by moving directly backwards. If the overlapping regions were placed at the front or at the back, this is not very useful, as when the ball is at the front, whether it is in the ball capture zone would have already been sensed by the top US. This makes our ball following function more robust, increasing its reliability.
As the SC card was inserted into Bob and Tim, they were immediately brought to life. They both charged for the ball, but despite their best effort, no goals were scored. How little chemistry they have. Seems like time for more strategies.
Oh, I know! Maybe we can implement a coordinate targeting function. This should be a versatile function to allow the robot to move from its current coordinate to any coordinate it wants to go.
Fear no more! I know exactly how to implement this. We can calculate the difference between the target and current x and y coordinates, or x and y distance the robot needs to move to reach its target coordinate. Taking the inverse tangent, we can calculate the direction the robot needs to move at. Of course, to prevent overshoot, we can slow the robot down when it's near the target coordinates. Let's calculate the distance between the target and current coordinates using Pythagoras' theorem. And we can not only determine how much to slow down, but also when the robot should stop targeting the coordinate and continue the rest of the program. This is because it is near impossible for the robot to reach its exact target coordinates, and time will be wasted for a level of accuracy we don't really need. Therefore, the robot stops targeting when it's within the certain radius of the target coordinate.
I thought of something too. Maybe let's put the goalie beside the striker. It blocks the goal very comprehensively, preventing the opponent from scoring.
But wouldn't the striker need to travel such a long distance just to reach the ball at a certain neutral point? This is definitely not very efficient if you want to score goals too. Remember, we need a balance between scoring and defending.
Oh, I know! What about putting the striker in front of the goalie? Since the opponent needs to maneuver the ball for a relatively long distance to reach the goalie should have enough time to move left and right, blocking the ball. At the same time, the striker is nearer to the ball and can take control of the ball more quickly, increasing our chances of scoring.
Yes, you're right. But I'm still confused as to what the positions are for. Please enlighten me.
Of course, these are the default positions of the goalie and striker. For the goalie, it will go back to its default position when the ball is far away from the goal, that is, the intensity of the IR sensed by the IR sensors are below a certain threshold. As for the striker, it will go back to its default position once it manages to score.
As for how the striker strikes, well, it will always move towards the ball when it senses the IR signal, no matter if it is strong or weak. Once it moves out of the boundary, it will quickly move back into the boundary.
Just to chime in, when the top ultrasonic sensor detects the ball, the robot automatically targets the center of the goal so that it does not score outside the goal. When it reaches the boundary, it will move back to its starting position.
Another thing we can do is to shift the front US of the goalie to the back instead. If the US in the y-axis is facing back, it is less likely to be blocked by the other robots, thereby making our localization more accurate.
And with that, Bob and Tim can happily play soccer, coordinating with each other and forming one of the best teams in the world. Here is the final code logic we used.
But they aren't perfect, so allow us to share some of the work we want to do in the future.
Indeed, firstly, Bluetooth communication. Currently, we leverage 𝗈𝒑𝒂𝒂𝒑𝒐𝒄𝒆 installed on 𝑰𝒏𝒇𝒍𝒄𝒆 to send messages from one 𝑰𝒏3 to another, which is known as daisy chaining. However, the Bluetooth signals are quite weak, and robots disconnect each other very easily, making Bluetooth communication not very reliable. We hope to improve on this to improve communication between bots, such that the robots can switch roles if convenient.
Secondly, ball following. As you can see in this video, The robot is very laggy when it is following the ball. This could be because of the many lines of code it needs to run in one loop. We had tried to reduce the runtime of each loop by reading off the sensors only once and using the same set of values for the whole loop. But the runtime has not greatly improved. Moving forward, we will try to reduce the runtime, possibly rewriting our code or exploring other platforms.
As Daisaku Ikeda, a famous Japanese philosopher, once said, "If everything is smooth sailing right from the beginning, we cannot become people of substance and character." We undoubtedly faced countless hurdles during the competition. Here's how he overcame them and produced such flawlessly working robots.
For example, we encountered many challenges when bracing the Omni wheels, and it was difficult to find a suitable position for bracing. And after failing 2 designs for the acrylic bracing, we made our own mold to melt and bend the acrylic strips.
And on the software side, we faced many issues such as the battery draining too quickly, the 𝑹𝒐𝒃𝒐𝒏𝒄𝒆 refusing to connect to our computers. But with some patience, we managed to get our robots working. We were also unfamiliar with the maths library of Python and did not realize the inbuilt trigonometric functions were in radians. A lot of research was required, but we were able to master the maths concepts required and apply them in our codes.
In this competition, many soft skills came into play, including flexible thinking, idea communication, and time management skills, just to name a few. If you are looking for a challenge and you want to learn something new, RoboCup Soccer is the competition to join.
And with that, our presentation has come to an end. Hope you've enjoyed the adventures of Bob and Tim and found our video useful, whether you're preparing for RoboCup Soccer or just learning some hardware and software.
Here's Tortilla Turtles signing off. Thank you for your kind attention.